All right, welcome back to the algorithm analysis slides. Let's keep on trucking. So we're talking about asymptotic growth of functions. If only we could have like a starting function, then use some other function to like bound it above. That's a bit simpler. That's essentially what big O is all about. So let's go there now. So we say that f is big O of g. You read it like that, or just f is O of g. Sometimes we say it like that. If g is essentially some constant times g bounds the function f. Okay. And so here's like the definition that you learned in CSCI 41. It's like, all right, f is big O of g when essentially g of n is bigger, right? G of n is dominating over f if you drop the constant factors that are out in front of your functions, and then also you only worry about large values of n, okay? So this is essentially what big O means. F is big O of g when this is true. When this is true. When you can multiply your function g by some constant, and have it eventually, not at the start, it doesn't have to be at the start, but eventually for some value, we call that n naught, for some value, c times g of n is always bigger than our f of n. It means it's bounding it above. So big O is talking about an upper bound. All right? So that's what that means. There's only a constant at the end of all your dropping constant factors. If it's just a constant, we call it constant time. You just get rid of the constant and just say it's 1. All right? So here's the real mathematical definition of what big O means. This is what it means. Like, why is this true? So first of all, f and g, they need to be special kinds of functions. They're functions that take positive numbers to positive reals. All right? That's how they need to be. That's usually what we're doing anyway. So then we say that f is big O of g if there exists, you see that? If there exist constants c and n naught such that f of n is less than or equal to, right? C times g of n is bigger than or equal to always f of n whenever n gets past that starting n naught value, okay? That's the idea. So in math, again, that's like there exists a c that's greater than or equal to 0, there exists an n naught such that these two could be flipped, but this one needs to be after all of those. So you need to pick these two such that always they work out for every n afterwards. Every n after the n naught, this is true. F of n is less than or equal to c times g of n, so it's always bigger. It's always bigger after the n naught. So we say that g is an upper bound for f. All right? Do you see that? So it's like, essentially, here's your function. Here's the other function. It's always bigger after a certain amount of time. It doesn't have to be at the start. Could be later. All right? But this is the one that's bounding it above. Right? So that means f of n, right, is always, it's big O of, so if this is n, 2n squared, it's big O of n squared, right? Because how could you prove this, right? You could be like, all right, according to the definition, I need to pick some things. So if you say let g of n, well, it has to be equal to n squared to prove that it's big O of n squared. And then you have to say, like, your constant out in front. Well, if it's 2 here, just make your constant c, and c equals 3, I think it'll always be bigger. Because like here's, I think that's what I'm drawing here anyway. It's like here is, let me redraw that with this in mind now. It's like, what is 2n squared? Maybe it's this one. And then this is like essentially 3n squared. G of n, if you multiply by that constant c, it's always going to be bigger. So there's, I don't know, there's like 2n squared. And here's like 3n squared. It's always going to be bigger. Maybe it's still 0 when it's 0. But it's always bigger or equal to 3n squared. So do you see how it's always going to bound it above? That's how that works. So it's growing faster after that constant multiplying. And the n naught, you can just make it 0 because it's always going to be bigger. See that? So that's why it's n squared. And it's also n cubed for similar reasons, n to the 4th. So this function, though we think of it as n squared, like technically according to the definition, it's also big O of n cubed. It's also big O of n to the 4th. Anything larger, that will dominate it, right? That's the idea. And then, yeah, the reason that this works, like if there's only a constant out in front, you can be like, it's big O of 1 because you can set your g of n, right? Your g of n to be, or g of x, whatever you want to call it, just equal to the number 1, which you could then multiply by any large constant that you would like. Doesn't matter. So that's beautiful. All right, so that's what big O means. Hopefully, it kind of makes a little bit of sense. Let me try to give you some more intuition. It's really talking about upper bounds. So it's saying that f is bounded above by g up to a constant factor asymptotically, which again may not make a lot of sense. But yeah, like my standard example is this one. That's the one we just kind of did. If you have f of x equal to 2x squared, it is big O of just x squared. See that? Got to keep the variables the same, though. You see that? F of x. We're talking about x's. It's not O of n squared when x is the variable. All right? So why is this true, right? Why do we say that this is true? Why do we care about big O? Why did somebody invent this? All right? It's essentially because when you zoom out, when n is large, these two functions, the function f of x equals x squared and the function f of x equals 2x squared, they don't really look that different. So here's a graphing calculator. We can be like, all right, f of x equals 2x squared. And then we'll have like g of x equal to just x squared. And you see, eventually, can I mess with these axes? Just be like, I guess that's fine for now. You see how if you zoom out far enough, I can mess with the axes some more maybe, but no, I don't want to deal with it. It's too much work. See how if you zoom out, like they're on top of each other. Red and blue is on top of each other. There's no real difference between these functions as you zoom out. They don't look any different. See that? That's essentially what big O means. It's like blue is on top of red right now. It does not really matter as you zoom out. That times 2 is not really doing much in the long run. All right, especially compared to larger, more complicated functions of different complexity. So yeah, here's an alternate definition if you've taken like a calculus class. I don't know if that's required for this class. I can't remember. But an alternative definition of big O is like f is big O of g if you take the limit as n approaches infinity and divide the functions, f of n over g of n, because this one's supposed to dominate it, right, as n gets large. You divide by the bigger one, the one that's supposed to be the upper bound, and then this better be less than infinity. It better be something that is finite, because that means g is really not letting f get too large. It's making sure that it's bounded. It's not running away to infinity. So that's another definition of big O, and that might be better intuition. But in general, we care about this being n squared rather than n cubed, right? That's a better, more tighter bound. And so here are the rules again. I'm sure like we learned this in CSCI 41, but here are the rules all over again to like take a function and like get the tightest bound for big O. So here are your rules. You drop your lower order terms, and then you also drop any constant factors in front of the highest order term. So as long as you find that, you can find your function, right? To find a g for the f's such that f is big O of your g. Okay. And then for this first one, let's kind of use the definition as well. Let's see why these rules work. Let's actually find a c and an n naught, even though that it's always going to work. And then we'll always be able to find one. Let's do this one. All right. So we're going to drop all the lower order terms. So as x gets large, x is the variable here. It's not n. These two don't really do much, right? So it's really the 2x squared. So that's the one that's helpful here. And then once you have just the largest factor by itself, you drop any constant factors in front of that highest order term. So you can drop the 2. And so that means f of x is big O of g, where g is x squared. You see that? That's your function. So we know now that f is big O of x squared because of these rules that we just applied. And let's prove it to ourselves why these rules work. Let's find our c. Let's find our n naught that make this work. Okay, so let's see, x squared, and then we have 2x squared minus x plus 3. So let's see, can I just like reset 2x squared, and then we have g of x equals just x squared. Oh, sorry, it's not 2x squared, it's 2x squared minus x plus 3. There. So x squared, we need to find like a constant out in front that we could multiply the g of x by to always make it bigger. I guess if this is a 2, like just make it a 3. It'll eventually get bigger, essentially. So like that could be our constant. Our constant can be c equals 3. And then what can our n naught be? Like it's okay if f, the red function, is bigger for a while when it's small. But you see, after a certain amount of time, our constant times g is always bigger. And this is where apparently it's 1.3, x equals 1.3, where they intersect. And so it's just like, all right, we can pick our n naught to be 2 then, because it's supposed to be an integer. So if n naught is 2, then for 2 afterwards, then you're good to go. Okay? So that's 2 afterwards. It's always that g, our constant, times g, or 3 times g is bigger than our original f. Okay? That's the idea, because it'll always work out. It'll always get bigger after that time. And you can write that out. You can prove it to yourself, like f of 2, what's that? It's equal to 4, 8 minus 2 plus 3. So that's 9. And then c times g of 2, right? It's going to be equal to 3 times, that's our c, 3 times our x squared, which is 2 squared is 4. So that's equal to 12, and that is totally bound in it. Beautiful. So how do I want to do this? Yeah, looks like that. Greater than or equal to. So yeah, that's essentially what it means to be big O. It's like, all right, eventually, like here's your weird looking function f. The goal of big O analysis is to find some other function, this is your f, some other function g that maybe at the start is not good, but in the limit, as it gets large. Take your g and you multiply it by some constant, it eventually wins off. It wins out. It bounds above f after some amount of time, and that first starting point where it always starts winning is called our n naught. All right? So that's that one. And now let's try these. Let's try these. So f of n is equal to 5n times log base 2 of n plus log base 2 of n. All right, so where are the lower order terms? It looks like this one's n times log n. This one's just log n, so this one's the lower order term. And then this one has a constant still out in front, so let's drop that. And so just immediately be like, all right, f is big O of n log n times log base 2 of n. See that? That's beautiful. All right, try these. Might be helpful to pause the video and figure this out. This may be a giant number, but it's just a constant. These things are bigger as x gets large. Eventually, x could be bigger than this number. You see that? So let's see, 27 and 15. 42 is the winner, the clear winner. And then, so those were the lower order terms we dropped. Then we'll drop the constant factors out in front of the highest order term. So it's just the 3. We're going to drop it. And so then, all right, we know immediately, according to our rules, this will always work. F is big O of x to the 42. All right? And you can always find, there's always a way, you can search for it, but these rules will work. You can always find your constant and your n naught, all right, to make it work. Eventually. Like just pick your constant to be, I don't know, pick your constant to be 4. Eventually it'll win out, all right, because this is just a 3. That's the idea. So, yeah, hopefully that makes sense. Here's another one. Let's do this really mathematically now. All right, so let's use the rules. We know that this is going to be this function is going to be O of n cubed. Let's prove that using the actual definition of big O, the mathematical definition of big O, this guy. All right, so let's find our c, find our n naught, and prove that for any n after the n naught, it really does work out. All right. So, well, let's prove it using the definition. So let's see here. How do I want to show this to us? One way to find your constant, right? An easy way to find a constant that will work, because you just need to find one. It doesn't matter, like, okay, it'll probably work if you had 3 and 3 was your constant. That's fine. Here's an easy way to find one that'll work and it'll be easier to prove. So again, we just need to find some constant. It doesn't matter which one. Multiple will work. So this is our original function, 2n cubed minus 4n squared plus 7. Do you see that, well, this is less than or equal to 2n cubed plus 4n squared? Just make it all positive, right? This will always be less than or equal to, perfect, plus 7. And then also, less than or equal to, do you see how, and this will also prove it just once and for all as well. This is an easy way to do the proofs. Let me move this over, actually. So I have changed nothing. I've just, like, this is a bounding above the original one. Do you see that? And just using math, I'm going to find a function that bounds it above. That kind of follows our definition of what big O needs to look like. So, okay, I got that. And then also, like 7 and 4n squared, See how you can make those n cubed and it will be bigger? 2n cubed plus 4n squared plus, or sorry, 4n cubed now, plus 7n cubed. You see how like I'm changing these to have n cubes next to them? That'll make it bigger, at least as long as n's not 0. Once n, right, this works. You see how this works? As long as n is 1 or bigger, this will always be true. Because like, so this would be 7 times 0, so that would be technically smaller. But once n is bigger than or equal to 1, works when n is bigger than or equal to 1. This will always be true, like it'll be bigger than or equal to. And then what is this, right? This is just a bunch of n cubes. This is all equal to 2 plus 4 plus 7 is 13? 13 n cubed. And so I found a function that looks like a constant times n cubed, ooh, out in front, and I've figured out exactly when that's going to be bigger, when it's always going to be bigger. Do you see how just with math, I've used the definition of big O. I need to find a constant and an n naught such that for every n after that n naught, my constant times my function is bounding above the original function. I just did that. Just be like c equals 13. There it is. N naught equals 1. There it is. Now you know why this function bounds above this function. This function right here bounds above this function. And that's what I needed to prove that f is big O of n cubed. I found a good constant, my 13. I found an easy n naught. Just kind of fell out of how I did this. That's a very easy way to make this work with the definition. Just like change it all, like make it positive if it was negative, and then make everything the highest order term. Like these were a bunch of n squareds and constants, make them n cubeds. That's an easy way to find a constant. All right, I hope that makes sense. So that, QED, beautiful. Let's try this one. Let f be a function whose domain is the positive integers and whose target is the positive reals. Let's show that if f is big O of normal n, then f is also big O of n squared. So like, you could make it bigger and it's not really telling you any information. It wasn't the tightest bound. Like this is n squared and n cubed and big O of n to the 4th. You can always go bigger. Any bigger function is fine. So let me show that to you. So all right, so that if this is true, then that is true. So it's like, right, this is a direct proof. It's like, assume this, assume f is big O, assume this, and we're going to prove this, show this. This is what we need to show. All right, so proof. We'll use the definition, of course. So, all right, let f be a function. We're assuming this. Let f be big O of n. All right. Then, what do we know? If f is big O of n, well, there exists a c bigger than 0. There exists an n naught such that this is true about g, about f and the constant times that function. All right. So, and this was the function g. G was just n. Right? Then, according to the definition of big O, there exists a c and n naught such that, I'll do st for such that for every n greater than or equal to n naught, then f of n is bounded above by my c times g of n, and g of n is just n, c times n. Right, so I have that. That's what I want. So that's what I'm assuming. And so I need to show that there is a way, there's a c and an n naught that make f bounded above by n squared as well. All right. So here is the trick. Let's keep the same c. Because again, to show this, I need to find a c and an n naught. Let's keep the same c for this one. Keep the same c. What we need to show then, if we keep the same c, we need to show that f is big O of n squared for that particular c. So we need to find that there is an n naught. There exists an n naught prime, a different one, maybe. Doesn't have to be the same one, such that f of n, right, it's bounded above by that same c times it's n squared this time, right? Because that's the function g, c times n squared. Okay? For all n greater than or equal to this n naught prime thing, right? A different n naught. So we need to somehow go from this to this. See that? Dun, dun, dun. What do we know? So this is going to be a key thing to notice. So if we have this, right? We have this. Can we somehow go to this as well? Can we, rainbow, take this and somehow transform it into this kind of thing? Do you see how if you just multiply this side by n, see that? If you just multiply this side by n, you've made something bigger if n is like bigger than 0. So notice this. This is our key. If n is greater than or equal to 1, then c times n is less than or equal to c times n squared. You see how that's true? If n is greater than or equal to 1. If it's 0, it's not true. If it's 1, then it's just like c is less than or equal to c. That's fine. But if it's 2, it's like c times 2 is less than or equal to c times 4. It's always bigger. So you can always multiply by an n. Essentially, you could multiply this by n as long as n is bigger than or equal to 1. And we already have this. We're assuming this. We're assuming that. We just need to show this somehow. And we can use it to show it. So this is our key. So what can we do? All right. Therefore, f of n, we really just did it. F of n is big O of n squared using our, we've got to pick a c and an n naught. Let's use primes for this one. C prime is equal to the original c. And our n naught prime, well, it's equal to, because I have fn is less than or equal to this, and this is less than or equal to this. If n is greater than or equal to 1, bringing those two together, I really have what I need to show this, right? N naught needs to be at least 1, right? It needs to be at least bigger than 1, and maybe this n naught as well, right? This original n naught that made this true, it may have been bigger than 1. So it's just whichever one was the larger one. It's the maximum of the existing n naught and 1. Right? Because if it was bigger, like you needed to be bigger than 1 anyway. But after that, like it's always, like this always holds after n is 1. So just like take the same n naught if you need to, or 1, whichever one's the bigger one. And so that shows, according to the definition, that it's also n squared if it was O of n. You can find another n naught very easily. You see that? Just using these two ideas. Like you get this for free when you're assuming it. You just gotta just use that fact. Just multiply essentially the right side by n, and that makes it bigger when n is bigger than 1. So yeah, that's the idea. So essentially, yeah, what we went from was, like essentially we had, kind of this idea. 1 is less than or equal to n, and then we multiply both sides by c. c is less than or equal to c times n, and then we multiply by n again. So we went from there kind of to there. This is kind of the idea. C times n is less than or equal to c times n squared. And this is always true. All this stuff is true when n is bigger than 1. Bigger than or equal to 1. Okay? So hopefully that makes a little bit of sense. One idea. Here, you try now. So let f be this. This function, prove that it's not true that f is big O of the square root of n. So it's not true. So you need it like a, you can't assume that it's true. It's not a direct proof anymore. It's like show that it's not going to work. Fn is equal to this. This is like big O of n, right? And square root is a smaller growing function than just n. So it can't be true that f is square root of n. I want you to prove that to me. And my hint to you is use proof by contradiction. So like assume that it is, show that the universe blows up, right? This is a fun example of a proof as well. So all right, assuming you tried it, what do we do? So we want to show that this is not big O of square root of n. So all right, by contradiction, let's assume that it is. Assume f is equal to big O of the square root of n. According to the definition of big O, what do we get? All this fun stuff. So there exists a c and an n naught, right? Such that, well, f of n, which is this, n over 100, f of n is less than or equal to c times the square root of n, because that's what g is, square root of n, for all n greater than or equal to n naught, and f of n is just n over 100. Right? So it's showing that n over 100 is less than c times square root of n for any n greater than this n naught. And then let's try to use this idea to create a contradiction. All right. So we've got, just from this idea, we know immediately that n over 100 we have as firepower that n over 100 is less than or equal to c times square root of n. Let's get the n by itself, so let's multiply by 100 on both sides. So that will give me n is less than or equal to 100 times c times square root of n. And then let's take both sides and divide by the square root of n. So let's divide by the square root of n on both sides. And this is going to cancel out this one and keep the n. What does that do? It's n divided by the square root of n. You know how this is it's equal to n to the 1 over n to the 1/2, and you just subtract exponents, so it's again n to the 1/2. So that's equal to the square root of n. See that? So that'll leave the square root of n on the left side less than or equal to 100 times c. Okay? And then just for fun, let's get rid of the square root. Let's just square both sides. So it's saying that n is less than or equal to 100 c squared. Okay? So just for math, from assuming this, we've proven that this must be true under this universe where f was square root of n, big O of square root of n, where we've proven that this must be true about n. All right? And what is c, though? C is a constant. But c is a constant. And n gets to vary. N gets to go to infinity. But c is a constant. Even if c is like 1,000,000, you can still find a bigger n. You can take whatever this is and make n equal that plus 1. N gets to go there, right? You can never, this variable can never always be below a constant. That makes no sense. That's a contradiction, right? So saying that, all right, this better be true for every n. It's always less than or equal to 100 times c, all that squared. No, just get one bigger than that. From then onwards, it's never going to be true. You can't bound a variable by a constant. That's not possible. So contradiction. Diction. Bam. And so that just proves, that's QED right there. Once you find your contradiction, you've proven that it's not true, right? It's not true that this is true. Does that make sense? That's a fun idea. Yeah, so in addition to big O, there are more. There was, what did I say? There's big omega, big theta. Really, we've been using big theta this whole time, more or less. But let's talk about all of them. So this is a different one. This is called big omega. It's another way to do asymptotic analysis of functions. But this one means lower bound. Big O meant upper bound. This means lower bound. So we say that f is big omega of some function g if, again, there exists constant c and n naught, but this time f is winning. F gets to be bigger. C times g of n is bounding below f of n. See that? Whenever n is bigger than n naught. So g is a lower bound. So it might be bigger at the start, but after some n naught, your constant times g of n is always below f of n. See that? It's a lower bound. It's a lower bound for f. So that means f of n, if this is f of n to n to the 5th power, that's bounded below by n to the 5th, right? It's a lower bound. It's bounded below by n to the 4th, a smaller power. N cubed, also smaller powers. But you can still get n to the 5th because it's just 1 n to the 5th is always smaller than 2 n to the 5ths. Or equal to. Lower bounds. So that's a difference. That's big omega now, okay? You see that? So, yeah, that's really it. It's kind of the opposite. That's big omega. Then big theta, might as well show the rest to you right now. Big theta is the combination. So we say that f is big theta of g if and only if it's defined to be true. That both of these things need to be true. They are interchangeable. F is big O of g, f is big theta of g if and only if it's both big O and big omega at the same time for g. All right. So you can expand both of those definitions and not use O and omega, but you just as easily could. So alternatively, what is that saying? It's all right, there are two constants, right? one for the big O part and one for the big omega part, and an n naught, and just take the bigger of the two original n naughts, such that f of n is sandwiched by g of n. It's bounded below by one constant times g of n, and it's bounded above by another constant times g of n when n is bigger than some n naught. Same function g, two different constants. They're sandwiching the f. C1 times g becomes, after n naught, you find a good n naught, it becomes a lower bound. And then after n naught as well, C2 times g becomes an upper bound. That's really cool, but that's essentially what it means. It's the combination, right? The same g is both an upper bound and a lower bound. It's like the tightest, best possible bound, okay? Upper bound and a lower bound, we call it the tightest possible bound. And usually, if people ask you, like in an interview, what is your algorithm? What is it in big O? Really, they're talking about big theta, right? Tightest possible bound. So that means you only have one answer. There's only ever one answer for big theta. We said f of n is 2n to the fifth. It is only big theta of n to the fifth, all right? Does that make sense? Because that's the only one. It's got to be the same power. You can pick like the constant 3 and the constant 1. That'll bound it above and below. Nobody else is going to do that, all right? It has to be n to the fifth. And then f of n equals to the n. That is big theta of n squared. Or sorry, 2n squared. That's only big theta of n squared. No just n. No n cubed. Because like that won't be both a lower bound and an upper bound for certain constants, right? So that's what big theta means. And anybody who ever asks you for big O really wants big theta. So like the one true answer for this one is n squared. It's not n cubed. It's not n to the fourth. Nobody cares about those. So it's like everything is big O of 2 to the n practically. So everybody really wants this one. This is the best one to understand. Big theta. It's kind of using big omega, so that's why we teach it too. But big theta is probably the most important one for the class. All right. So yeah, here are some questions for you. So give this. Give me the rate of growth for each function f by giving a function g such that f is big theta of g. And you can really just use the rules. These rules will give you the big theta pretty much. All right, but now you know. It's got to work for big O and big omega. It's got to be a sandwich. Tightest possible bound. So give the tightest possible bound, give a g such that f is big theta of your g for each of these a, b, c, and d. Okay? Well, let's see here. So let's do a. Well, taking the log of a log and a 5, those are smaller terms than an n times a log, right? And then you have a 9 out in front of that, and just drop the 9. So this is really the rules just work. This is big theta of n log of n. So I didn't even specify what this log base was. Maybe it's log base 2. I don't know. Write log base 2 there if you want. But really, what you could be saying, yeah, you really don't need this base. That's why I didn't include it there originally, actually. So let's do this one, though. So what's going to happen here? This is, again, that's pretty much done for you. Like, you could say that the answer is n times log base 37 of n. But actually, this is big theta of n times log base 2 of n as well, or log base anything of n. So people just write, and you'll see this in the literature, they just say n log n times log n. They don't actually put a base for their logarithm, all right? So this is b. The base doesn't matter because it's just off by a constant factor to convert bases for logarithms, right? Base doesn't matter, and we're getting rid of any constant factors anyway. So you can just write it without a base. It doesn't really matter because do you know that log base 2 of x, right? You can, I forget exactly how to do this, but log base 2 of x is equal to, like, you can turn that into a log base 3 of x. And you just have to multiply by log, I don't remember. It might be log base 2 of 3 or log base 3 of 2. I can't remember which one's the right one. But whatever this is just a constant. And so it's just off by a constant factor no matter what the base you pick for your logarithm. It doesn't matter. And so we get rid of that anyway. And so people just like to write n log n, and that's why. That's why it's allowed. You see that? So I hope that makes sense. And then here, which one's the bigger term? It's not this one, actually. It's the 1.1. It's a very slow one, but exponential functions. When n is in the exponent, it's always going to be the one that wins. This is big theta. And you kind of got to keep this when it's n to that power. You have to keep it there. So it has to be 1.1 to the n. You can't just like make it 1 to the, sorry, not 1 squared. Big theta of 1.1 to the n. It's not the same as like 2 to the n. It's not the same as, of course, not the same as 1 to the nth power. It's 1.1 to the n. You got to keep the 1.1, right? Just like you kept the cube in this one. You didn't make it anything different. So those are the lower order terms, and this is just immediately big theta of n cubed. That'll always give you the tightest possible bound if you just do our stuff. Follow this box. It's really giving you big theta. Should I be writing that somewhere? So really big theta. Okay, so yeah, that's very nice of it that works. So hopefully this makes some sense. It's really just thinking about what the highest order term is. Maybe you didn't understand the logarithm thing, but that was a teaching moment. But now you do. Here's one more. So this one I want you to prove. All right, so here's the definition of big theta. Like all this has got to be true. You can alternatively show that it's both big O and big omega. That's also fine. But maybe we'll do it this way when I do it with you. But let's see, what do I want? Let us have this function f, n cubed plus 3n squared plus 4, prove that f is big theta of n cubed. Like it makes sense that it is, right? I want you to, though, find the values. Find c1, c2, and n naught, and prove algebraically that it works for big omega and big O. Right? That it follows the definition. Okay? That works for both of them. Okay, so I have to show that, the big omega part. I need to show that there's a lower bound when I have n cubed. I need to show that there's an upper bound when I have n cubed. So I need to be like, all right, n cubed plus 3n squared plus 4 is bounded below by n cubed by some constant c1. And you can just take that to be 1, right? That's easy because it's like that one's always bigger because it's like adding 4 to it no matter what, even if it's 0. That's perfect. This holds, right? If c1 is 1, like n cubed is always less than or equal to n cubed plus 3n squared plus 4 for any n, right, that's bigger than or equal to 0. Works for every n greater than or equal to 0. That's perfect. And just like that part gives me the big omega, right? Therefore big omega. Like this is big omega of n cubed. We also need to show that it's an upper bound. We need to show that n cubed plus our original function, 3n squared plus 4 is bounded above now by some constant 2 times n cubed. All right, and let's try and do the thing that I was showing you before. Which one was it? This one. Let's do this kind of idea because that'll give us a very easy way to find our n naught as well. Okay. So, okay, let's do that kind of process. So like n cubed plus 3n squared plus 4 is less than or equal to, right? Let's just change all these to n cubeds. This is true a lot of the time, plus 3n cubed plus 4n cubed. It's not true. This is not true when n is 0, but it's true when n is 1 or bigger, right? This works when n is greater than or equal to 1. I hope you see that. And what is this but just 4, 5, 6, 7, 8 n cubeds? And so there's an easy constant. And so that can be our C2 right there. C2. And so that can be our constant. Our n naught for the big O part can be bigger than or equal to 1, and this always holds, right? That's how we found the 8. So therefore, it's big O. This is big O of n cubed. And so now I've shown that it's both big omega and big O of n cubed, and therefore I can pick my C1s and my C2s. C1 is 1. C1 is 1. C2 is apparently 8. That worked for that one. And then my n naught, what's my n naught that's going to work for both of them at once? It's just like, all right, this worked when n was greater than or equal to 0, and this part worked when n is greater than or equal to 1. So they'll both work together when n is greater than or equal to 1. You see that one? Like just take the maximum. So let's set n naught to 1. That'll, of course, like the first one will still work. So therefore, it is big theta. So this is big theta of n cubed. QED. I hope that made sense, and I hope that's similar to what you got. That's how you'll do it. That's how you can prove that something is something else. And so this is all about, right? The reason we're learning about any of this is because we're trying to make functions that describe the running time or the memory usage of our algorithms. And so we need to talk about algorithm complexity, all right? So we're ready. Let's do it. So we want to learn how to analyze algorithms in some way. We have to like keep track of their computational complexity, like how complex are they, for some definition of complex. So this has to do with the amount of resources that is being used by your algorithm as it's running on a certain kind of input. And resources is a vague word. There's a bunch of different kinds of equivalent resources that you might care about, or maybe not equivalent resources that you still might care about each of them. We have to get even more specific now. We can talk about the time complexity of an algorithm. And that's how much time it needs to run. That's pretty obvious, right? So we're going to count the number of essentially operations that it's taking, the basic operations. And I'll underline that because what I'm trying to say there is like instead of like counting time, like my algorithm takes 42 minutes to run, that's horrible because you might have like a 1.5 gigahertz processor. That'll of course run your program twice as slow as a 3 gigahertz processor. You see that? Because this runs 1.5 billion instructions per second. This one runs 3 billion instructions per second, where instructions are like basic things that the CPU could understand and do in one clock cycle, we say. So you'll have to wait until CSCI 45 to fully understand what I just said in that sentence. But yeah, count the number of something else, and that'll like be a better way to measure your algorithms. All right, and that's kind of what you did when we learned about it in CSCI 41. And then space complexity is also important. That's the amount of memory that you're using as you're running your algorithm, because we don't have a bunch of memory in our program. Like maybe you're getting a big long list of n things from the user, and you have to store them, right? So essentially, you're going to count the number of bytes that you're using to store your things. That's one way to think about it, right? So as you're analyzing an algorithm, you're essentially coming up with like a function that tells you for the input size how many basic operations your program's going to take, or for an input size how many bytes of space your program's going to use. Come up with a function that describes how the amount of resources changes as your input size varies. Maybe it doesn't change. Maybe it's a constant time algorithm then. And then you take that function that you just generated. It's now something and that's mathematical. You can do your asymptotic analysis on it. You can do your big theta. Do whatever you want. Okay, that's where we're going. And so here's just an example to finish this off. Let's analyze the running time. So we care about the time it takes to run these things, of summing all the elements in a vector. So here I am for once using C++ in lecture. So here's a function that takes a vector. Probably should have taken it by constant reference, but we take it, and let's say that vector is of size n. Because we need to do an analysis based on the size of the vector, right? So what we want to do now is come up with a formula, based on n though, for the number of basic operations. That's the term I like to use. The number of basic operations that this algorithm takes. It takes up when it runs. And so what is a basic operation? I'm trying to model things that the CPU can do really quickly in one clock cycle, we say. But here's like the CSCI 26 version of that. Let's say that a basic operation is an assignment statement, a return, any kind of mathematical operation like a plus, a minus, computing an answer, looking up a variable out of memory because it lives in memory, right? Something like that. So pretty much basic operations are like just like a line of code that doesn't loop or call any other functions. And we can assume that like v.size and v.at, those are constant time things. So those are like one basic operation, let's say, right? So with that in mind, let me like do that for you. Let me give you an example of all this, and then I'll ask you to do it later. So like this is shoving a value into the sum variable. That's an assignment. So let's say that is one basic operation there. And then this one It has to compute v.size, so it has to ask it for the size. Let's pretend that asking for the size of a vector is one basic operation. It's some constant number though. Let's say that it's 1, and then we're going to assign the answer into n. That's another thing to do. We have to assign the answer after we get the answer back. That's 2 operations, 2 basic operations for that line to run. And then now here we have a for loop. There's a reason I put all these on different lines. We have a for loop, and it's going to do a bunch of stuff, right? How many times is it going to iterate, for example? Well, a for loop only ever runs this line once, won't it? So int I equals 0, that's going to that's the initialization of the for loop. That line only ever runs once, and it's just like putting a value into a variable. It's an assignment. So that's one basic operation. And then whatever this all is, do you see how it's going to be repeated because I is going up to v.size minus 1? So that's repeating all of this n times. It'll also repeat this condition one more time, but we'll get to there in a second. So this is going to get repeated n times, and like how many basic operations are these things? Let's figure this out together. So, all right, we have look up the value of a variable. Call this, get its answer back. Let's pretend that that's also one basic operation. And then compare. That's like a mathematical operation. So it's 3 basic operations, let's say. Really, you'll understand soon that this doesn't really matter. And you know now, hopefully, after CSCI 41, that counting like this, being very specific, doesn't really matter. But it's good to practice. So it's like 3 basic operations to do that once. Then also I++, which is secretly I equals I plus 1. So it's like look up I, add it to 1. It's another basic operation. That's 2 so far. And then shove that answer back into I. That's 3 basic operations total. That's 3 there. And then this one, all right, sum plus equals that. It's like, all right, you have your sum equals, that's one assignment, one basic operation to do the assignment, equals sum. So look up sum. That's an extra basic operation. Call this, let's pretend that v.at_i takes 1 basic operation, so that's the 3rd thing. And then the addition, right? The addition that we're then going to put in the sum variable. That's a 4th basic operation. So that's 4 basic operations total. And then, so that's going to be repeated n times. Then returning sum is just like look up the value of a variable. So look up and then return, both together in that line. So that's going to be 2 basic operations. So again, it doesn't really matter your counts, but here's kind of what we just did. It's 1 plus 2 plus 1. 1 plus 2 plus 1. And then we're repeating all this n times. So it's 3 plus 3 plus 4 n times. 3 plus 3 plus 4. And then also, remember that loops, they need to like look at when I is equal to v.size, it needs to stop the loop. This needs to become false. So it needs to actually check this condition one last time. So it's really going to do this 3 basic operation thing one last time to stop the loop, and then it'll return sum, which is 2 basic operations. And so essentially, we've just come up with a formula, an f of n essentially, that talks about the running time for this vector sum operation, the number of basic operations it'll take as the size of the vector gets larger. So n is the variable size of the vector. This is equal to, oh gosh, how many n's? 7, 10 n's. Cool. Plus 3, 4, 5, 6, 7, 8, 9. Plus 9. 10n plus 9. So that's my f of n. And then we can analyze that. We can do big theta on that. This is a linear time algorithm, right? It's big theta of n. We just analyze that running time. Does that make sense? That's going to be, that's kind of what you do. Really, you don't have to really think about this. You just be like, instead of thinking about it this way, you can be like, this is constant. This is like O of 1. So you can just think of it as 1 basic operation. This is constant, O of 1, O of 1, dot, dot, dot. Stuff like that. That also is, it's going to lead you to the right analysis, but not like, you don't have to like go through this anymore if you don't really want to. But this is like the reason why it is big theta of n. It's taking essentially on the order of n basic operations to compute this answer for a vector of size n, to sum it all up. Okay? So that is the idea. This n was, again, the size of the vector. So let me write that one last time. Size of vector. And I think that is everything. So we're going to do more about this later, but we had to go through this sort of complexity analysis stuff, asymptotic analysis, asymptotic growth stuff, big O, big omega, big theta, so that we can get to here. All right, that's this is where it comes back to computer science. All right. So that's where I want to stop for the day. Hopefully your brain isn't too fried. Do yell at me if you have any questions, and I will see you next time.